birds have a bucket speed. So for this Physiology Fun Day presentation, I'm going to try and correlate a concept that we use in aviation and kind of show how that concept is also used in birds when it comes to their metabolic rate and flight speeds, and how we kind of do the same thing when we're talking about our power availability and our best single engine airspeed, or our bucket speed. What is a bucket speed? A bucket speed, or best single engine airspeed as we call it in the helicopter world, is defined as the speed where the greatest excess of unused power exists. So this becomes very important to me as a pilot. If I lose an engine and I'm only down to single engine flight in a Chinook, and let's say we're pretty heavy, we've got a lot of weight on the aircraft, I want to know what airspeed I need to slow down to in order to conserve as much power as possible, so that in case I need to perform a maneuver to get out of harm's way, either crashing into an obstacle or crashing into another aircraft or crashing into the ground. Best single engine airspeed, or bucket speed, is a point where the induced drag and parasitic drag cross over. And this is where they kind of produce the least amount of total drag on the airplane or aircraft. So induced drag is going to be the aerodynamic drag caused on an airfoil or a wing or a helicopter blade, which is caused by lift. So as that blade or that wing speeds up through the air, it causes the angle of attack or the angle of incidence. Basically what it does, it causes the wing to rise up, and that kind of exposes more surface area to that wind, that wind coming at it, which creates that induced drag. Parasitic drag is the drag caused by extra things on the aircraft, antennas, modifications, landing gear. Airplanes don't, they bring their landing gear in. Helicopters, we don't. We leave our landing gear out all the way because we don't go as fast, so we don't really need to worry too much about that drag. But that's what parasitic drag is. It's all that extra drag. So, and as I slow down, right, if I'm slowing down, I'm taking all that, I'm reducing that induced drag, I'm reducing that parasitic drag, and in turn, reducing the total drag on the aircraft. So if I have less speed than this single engine airspeed, let's say I slow down too much, I slow down below my best single engine airspeed, any power that I provide to the aircraft, the aircraft is going to have to overcome that excess drag in order to create that lift and get me out of harm's way or a situation I don't want to be in. Now, on the other end of that, the excess speed, it's not too bad, because if we do have at least one healthy engine and we're not too heavy, I can slow the aircraft down, which is the whole point of this. I'm slowing the aircraft down and exchanging that airspeed for lift. So as I slow the aircraft down, the drag decreases, lift capabilities of the airframe or the aircraft or anything increases. So, and which you'll see in the next slide, as you go faster, the more drag you have. As you go slower, the more drag you have. But once you hit the sweet spot, that's where everything will come together for you. So here's a visual representation of bucket speed, or best single engine airspeed. This is one of the graphs that they show us at flight school. It's one of the first things they show you to help you understand bucket speed and best single engine airspeed and different types of drag. So you see in red at the top, actually, let's go back. So you see you got total drag on the y-axis, you got forward airspeed on the x-axis. So in the red, you got total drag. In looks like magenta, you've got induced drag, which we talked about. Induced drag is the increased drag on on a wing or a helicopter blade due to lift. In blue, you've got profile drag, which profile drag is just going to be the normal drag of the airframe based on its aerodynamic design. And then you have in green, you've got that parasitic drag, which we talked about, any extra modifications or anything sticking outside of the aircraft, which is going to cause, which the wind is going to hit and cause you to have issues. So you can see the yellow dotted line, that kind of showed that's your bucket speed. And that's kind of why it's called bucket speed, because it kind of forms a little bit of a bucket. Everything kind of dips down, right? And it kind of shows you where your best single engine airspeed or bucket speed will be, depending on, your the weight of your aircraft, the type of aircraft you have, how much power you have, and the ambient environment, so temperature and the density, altitude of the air that you're going to be at. And that yellow line too isn't stationary there either. It's going to move to the left or the right depending on those factors. So with that last graph in mind from last slide, and looking at these two figures, which I took from our textbook that we're using in lecture, you can see in figure A that the predicted relation from aerodynamic theory looks almost exactly like the total drag line from the previous slide. Looking at figure B, looking at the budgie and the magpie specifically, you can see that though their empirical data definitely shows that they have a bucket speed or a best airspeed that they like to fly at in order to maximize their airspeed and also help be most economical for their metabolic rate. This shows that they do have a bucket speed, and they perform just like aircraft do, right? When they're going at a slower flight speed or airspeed, their metabolic rate is high. And for us in an aircraft, our power would be high. Our power is basically our metabolic rate using our power setting and how much fuel we're using. And then as they speed up, that drag comes down. Our drag comes down as we speed up, and they get to a point where they have their most efficient airspeed, to where they have a good metabolic rate, very, very economical for the airspeed that they're going. And then you also see too, just like that last slide, that as they speed up, that drag increases and their metabolic rate increases. And you can't really see it for the other three birds, the European starling, the rock dove, and the laughing gull. But they too, if you look at them closely, their lines dip as well, just not as dramatically as the magpie and the budgie do. So here's my works cited that I used to kind of put this presentation together. And this is just kind of a down and dirty, showing the correlation between the techniques and concepts we use in the aviation world and how birds use the same techniques. And I just thought it was very interesting to see that. I know it's kind of common sense, to think about it that way, but I think it's just very important to realize that for modern day issues and modern day problems that we might come across, that sometimes looking into nature and looking into biology might give us those resources to be progressive and move forward in the technology realm. So if you guys have any questions, feel free to ask them in the discussion board, or if you want to comment on this YouTube video, I'll be more than happy to answer any questions that you guys have. Thank you. I hope you guys are having a great time off doing this online work, and stay safe and stay healthy.